Hey everyone, welcome back to The Explainer. We've got a really fantastic journey ahead of us today. We're going to build our understanding from the ground up, starting with the very basic definitions of physics, working our way through exactly how we measure reality, and ultimately arriving at the invisible, underlying forces that basically govern the entire universe. So if you've ever wanted a structured, no-nonsense guide to how our physical world operates, you're in the exact right place. Okay, let's dive into this. We're going to start with physics and human society, then get right into measuring the physical world, move along to understanding straight-line motion, and finally wrap it all up with the laws of force. All right, part one, physics and human society. Let's explore the foundations of natural science. It's super easy to think of physics as just a bunch of abstract math on a dusty chalkboard. But honestly, it is the exact reason ancient monuments like Fossilus Castle stay standing, and it's literally how the smart device you're using right now actually works. The word itself comes from physis. That's ancient Greek for nature. And really, that hits the nail on the head. Physics is just the branch of natural science that tries to figure out the fundamental mechanisms making our universe tick. So whether we're talking about a simple fan spinning in your living room or a massive rocket blasting into orbit, physics is just us studying nature's rulebook. Now, nature is pretty vast, right? So physics is broken down into a bunch of highly specialized branches. We've got mechanics dealing with motion and force, acoustics for sound, optics for light, and thermodynamics for heat. Then there's electromagnetism, nuclear physics diving into the tiny atoms, and astrophysics looking at the entire cosmos. It kind of just shows you the massive scope of the whole shebang. We're talking about a field that scales all the way from invisible, microscopic particles up to the very edges of the known universe. And look, we wouldn't have any of this modern understanding without some absolute giants of history. Isaac Newton laid down the foundation of classical mechanics and gravitation. Michael Faraday quite literally changed the world with the first electric generator. James Prescott Joule connected heat to mechanical work. Marie Curie, absolute legend, she pioneered radioactivity and basically birthed modern nuclear physics. And then Albert Einstein comes along and completely flips our view of space and time with relativity. Together, these minds totally transformed classical physics into the complex modern physics that drives today's technology. Moving on to part two, measuring the physical world. Let's look at the tools we use to quantify the universe. So if we want to actually understand all these vast concepts passed down by physicists, we need some really accurate tools. In physics, everything we measure gets tossed into one of two buckets: fundamental quantities and derived quantities. Fundamental quantities are basically your baseline. They are things you measure directly, like figuring out length with a meter stick or time with a clock. Derived quantities are, well, exactly what they sound like. They're calculated by combining those fundamental ones. A perfect example is speed. Speed is just length divided by time. It's like a giant puzzle, right? Every complex measurement in the universe is simply built out of these basic fundamental pieces. And here's the universal alphabet we use to describe all of it: the 7 fundamental SI units. The International System of Units. We use the meter for length, the kilogram for mass, the second for time, the Kelvin for temperature, the ampere for electric current, the mole for the amount of substance, and the candela for luminous intensity. No matter where you go on Earth or what obscure branch of physics you might be studying, these 7 units are your absolute standardized foundation. Now, what's really interesting about this slide is this massive number: 299,792,458. What on earth does that have to do with measurement? Well, for our measurements to be perfectly universal, they have to rely on absolute constants of nature. A single meter today isn't just a wooden stick sitting in a museum vault somewhere. No way. It is precisely defined as the exact distance light travels in a vacuum over 299,792,458th of a second. Just let that sink in. It's exactly that kind of mind-blowing precision that makes modern physics possible. All right, before we start moving things around, we got to get straight on the difference between scalar and vector quantities. Scalar quantities are super straightforward. They are completely described by just their magnitude, meaning the amount. Think of your mass or the temperature outside. That's it. But vector quantities, they need a magnitude and a specific direction. So if I say a car is driving 50 kilometers per hour, that's a scalar. But if I say that car is moving 50 kilometers per hour east, boom, that's a vector. Adding that direction changes the whole game, as we're about to see. Which brings us to part 3, understanding straight line motion. Let's see how objects actually move through space and time. Okay, we've got our measurement tools firmly in hand, so it's time to put them to work. Let's start with a classic matchup: distance versus displacement. Picture this. A student walks from their house to school, which happens to be exactly 1 kilometer away. After the bell rings, they walk that 1 kilometer right back home. The distance they traveled, the total path length, is 2 kilometers. Makes sense, right? But their displacement, which is the overall change in position from where they started to where they ended up, is exactly 0, because they finished in the exact same spot they started. It's a brilliant way to see how your total distance can be super high while your total displacement remains exactly 0. Distance is scalar. Displacement is a vector. Now, building on that, we gotta talk about speed. Average speed is simple enough: total distance divided by total time. But let's be real. Actual real-world road trips involve speeding up, hitting the brakes, and sitting at red lights. That is exactly where instantaneous speed comes into play. It's the exact speed an object is moving at one specific microscopic instant in time. It is literally what you see when you glance down at your car's speedometer during a trip. It doesn't care about your whole journey. It just tells you how fast you're going right now. Let's move to and see how this builds, because motion is basically a chain reaction. Step 1. An object's position changes over time. That rate of change? We call that velocity. Step 2. That velocity changes over time. So speeding up, slowing down, or swerving to a new direction, that rate of change is what we call acceleration. It flows right down the line. Position changes to create velocity, and velocity changes to create acceleration. And one of the most powerful tricks physicists use to understand all this is graphing it out. It makes the math incredibly visual. If you're looking at a position time graph, the slope of the line directly represents the average velocity. Basically, how steep the line is tells you exactly how fast the position is changing. Then, if you look at a velocity time graph, the slope of that line gives you the acceleration. So just by eyeballing the angle of a simple line on a graph, we can instantly understand both the speed and the acceleration of an object. Pretty cool, right? All right, final section, part 4, the laws of force. Time to talk about the invisible pushes and pulls of the cosmos. So, up to now, we know how things move. But why do they move? What are these invisible pushes and pulls acting all around us? Well, a force is simply a push or a pull that changes an object's state of motion. And we split these into 2 distinct camps. First, contact forces. These require actual physical touch. If you push a heavy box across the floor or friction drags on a rolling ball, that is a contact force. But then we have non-contact forces, which honestly seem a little like magic. They act from a distance without touching anything. Think about gravity pulling a thrown basketball back down to Earth, or a magnet snagging a paperclip from across the desk. These forces literally shape the entire universe without ever making physical contact. Now, if we really want to grasp forces, we absolutely have to talk about inertia. Inertia is essentially matter's natural stubbornness. It's the tendency of an object to just keep doing exactly what it's already doing, whether that's sitting perfectly still or cruising in a straight line, unless an external, unbalanced force steps in and makes it change. And you literally experience this all the time. Imagine riding in a moving car, and the driver suddenly slams on the brakes. Your body jerks forward, right? Why? Because your body has inertia. It stubbornly wants to keep moving forward at the speed the car was just traveling, until your seatbelt acts as the force that stops you. And all of this perfectly sets the stage for the big one, the ultimate climax of our explainer, Isaac Newton's 3 laws of motion. Law number 1 is the law of inertia. An object at rest stays at rest, and an object in motion stays in motion unless acted on by a net force. Law number 2 is the math. Force equals mass times acceleration, or F equals ma. Basically, the heavier an object is, the more force you need to accelerate it. Simple enough. And law number 3 is action and reaction. For every action, there is an equal and opposite reaction. If you shove a brick wall, that wall is pushing right back on you with the exact same amount of force. It's a two-way street. So the crucial point is understanding the difference between mass and weight. Honestly, people mix this up all the time. Mass is your inertia. It is the actual amount of matter inside you, and that never ever changes whether you're standing on Earth or hanging out on the moon. But weight is simply a force. It's calculated as W equals mg, your mass multiplied by the acceleration of gravity. Because the moon's gravity is way weaker than Earth's, your weight completely changes up there. Even though your mass, the actual amount of you, stays exactly the same. Wow, okay, we have covered a tremendous amount of ground today, from the absolute basic units of reality all the way up to the laws of motion governing the stars. But before we wrap up, I want to leave you with a really provocative, kind of mind-bending question based on Newton's third law. If every single action in the universe requires an equal and opposite reaction, what exactly is the universe pushing back against? Think about that for a while. Keep questioning everything, and I'll see you in the next explainer.